Okay, so for scenario 1, A2 equals 20 with a doubling time of 32 years. I determined that A34 equals 40 because 2 plus 32 equals 34 and 20 doubled is 40. The explicit formula is AN equals A2 times R to the n minus 2, where R is the common ratio. Using A34 equals 40, A2 equals 20, and n equals 34, I solved for R to find a recursive and explicit function, as R, or the common ratio, is used in both the recursive and explicit formulas. Solving for R resulted in R equal to the 32nd root of 2, or 1.0219. Next, I plugged my value for R into the recursive and explicit formulas, and also plugged in my value for A2, 20, into the explicit formula. My recursive formula was f of x is equal to a sub n minus 1 times 1.0219, where a sub n minus 1 is the previous term. My explicit formula was f of x is equal to 20 times 1.0219 to the power of n minus 2, where n is the number of years. To convert my explicit formula to an exponential function in the form of y equals ab to the x, I first changed the 1.0219 to the n minus 2 to 1.0219 to the n over 1.0219 to the second. This was because I wanted to get the 1.0219 to the n by itself to convert it to the form ab to the x. Then I divided 20 by 1.0219 to the second in order to get a in the exponential formula. And I got 19.1521 for my a value. My exponential formula then reads y equals 19.1521 times 1.0219 to the x, where x is the number of years. This scenario demonstrates growth because 1.0219 is greater than 1. Therefore, each scenario demonstrates exponential growth because the value increases. With a growth factor of 1.0219, the annual growth rate is 2.19%. To find the exponential function with x in months, I divided 0.0219 by 12 in order to convert the annual growth rate to the monthly growth rate, and there are 12 months in 1 year. My exponential function is now f of x equals 19.520 times 1.001825 to the power of x, with x equal to the number of months. The monthly growth rate is then 0.1825%, as 0.001825 is 0.1825%. Here are my two functions graphed on Desmos. The red line is the function with x in years, and the blue line is the function with x in months. The difference between the graphs makes sense because with x in months, the growth rate is compounded monthly rather than yearly. This causes the result to increase more rapidly over time than when the growth rate is compounded annually. For scenario 2, there is $10,000 with a 6.54% monthly interest compounded continuously. To write an exponential function, I use the equation a equals p times e to the rt, where p is the initial, r is the rate, and t is the time, and e is Euler's number, which is 2.718, and the a equals the total. I plugged in 10,000 for p and 0.0654 for r. My exponential formula was then a equals 10,000 times e to the 0.0654 to the x, where x is the number of months. To find the effective monthly interest rate, I use the equation r equals e to the I minus 1, where r is the effective interest rate, e is Euler's number, and I is the interest rate. I plugged in 0.0654 for I and solved for r to find the effective monthly interest rate, and I got 6.76%. To find the effective annual interest, first I raised 1.0654, the growth factor, to the power of 12 and subtracted 1 from this value to find the annual rate, 113.87%. I did this to find the annual interest rate, which I can plug into the effective interest rate formula for I. I then plugged in 1.1387 for I in the formula r equals e to the I minus 1 and found the effective annual interest, 212.23%. I found an exponential function in the form y equals ab to the x, where x is the number of decades, by using my exponential formula with x in months. 10,000 times e to the 0.0654 to the x. There are 120 months in a decade, so I multiplied the monthly rate by 120 to find the rate per decade. My exponential formula was then y equals 10,000 times e to the 7.848 to the x, where x is the number of decades. To find the unit of time that has an effective interest rate of 520, I first calculated the interest rate using the formula r equals e to the I minus 1, where r equals the effective interest rate and I equals the interest rate. I substituted 5.2 for r and solved for I. And for the interest rate, I found 182.49%. I then had to find the unit of time with the effective interest rate of 520%, and I used the formula I used to convert the monthly rate to the annual rate to isolate t, or the number of months. My equation was 1 plus 0.0654 to the t minus 1 equals 182.49%, where 1 plus 0.0654 was the monthly rate. I then solved for t and found that 16.3926 months has an effective rate of 520%.